Hello, my name is Jim, and today we're going to be talking about relays. And relays are found in a lot of industrial circuits and also in many other non-industrial circuits too. Basically, it's a magnetically operated switch, just like this wall switch, and it can be large or small depending upon the applications. It can switch high voltages and or high currents, or low voltages and low currents. So that's what we're going to start with. And what a relay basically looks like is you have a pole piece, and that's this guy right here with turns around it, and you can kind of see this on this relay right here. This is the coil that produces the magnetic field in the ferrous pole piece. So this is actually going to form a magnetic circuit, which is not unlike that of an electric circuit. And it switches contacts. Is when it activates, it'll pull this down. And maybe you can hear the click or not, but what that's doing is it's closing two contacts and opening two contacts, and we'll talk more about what these contacts are referred to a little bit later. I have a 4.5 kilowatt generator in the house here. It's not enough to power the whole house, so I take selected lines like that going to a refrigerator and certainly the well, and place this in the circuit. So when the generator comes online, it activates the circuit and switches both neutral and hot, or in case of the well, the both hots for the 220 20 volt line. So I've never had to replace one of these, and it's been in use in this house for, I don't know, 20-30 years. I live in downtown no place, so a generator is very important. Anyway, this is what the contacts look like, and this is shown in the relaxed position, the non-operated position. And the piece that moves here, and that's what I just clicked on the relay, is called the armature, and it has a little spring on it that pulls it open. So when we pass current through this, we have to build up a strong enough magnetic field that can overcome the force provided by the spring. In addition, make sure these contacts really mate well. So the armature is connected mechanically to the part of the relay, part of the magnetic circuit, and when this gets activated, this guy simply pulls down, which brings this guy down to here. Now what you're looking at here is called a Form C contact. We'll get into that in a minute. And there's actually three connections on this. When the relay's off, as in not operated, we have a continuity path from terminal 1 to terminal 2. And when the relay is operated, this green line will go down to this point, and we'll have a continuity path between 2 and 3. So we have different types of contact forms for different types of applications. So in contact terminology, and this is a very important topic for PLCs also, because they control a lot of relays, especially like on production lines and so forth, is we have what's called a Form A contact. This is called normally open, and basically it's off until you activate the relay, which is kind of makes sense. Its symbol in PLC looks like a capacitor, but it's not. So when you get into the PLC course, you'll be seeing these all the time. Second is a Form B contact, and a Form B is when the relay's not operated, we have continuity, and when it is operated, we turn it off. Its symbol in PLC looks like a capacitor with a line drawn through it. Finally, we have Form C contacts, which is basically a combination of Form A and Form B, and we're free to wire this if we choose as Form A or as Form B. Now, we can have multiple contacts. For examples, what you can see here perhaps is that there are two sets of contacts on this here, and they're both Form C. So in the textbook, the distributor's manual, is this would be referred to is a 2FC, 2 Form C on one relay core. So designations that you'll be running into are things like 2FA, which simply means there's two sets of Form A contacts that are operated by the same core, or say 3 FCs, where we're talking about 3 form C contacts operated by the same core. Now, the more contacts we put on it, basically the larger the magnetic field, because it's actually moving more stuff that has to make a good solid contact. So for uses, we have low voltage, low current devices can switch high voltage and high current devices. Now an example of that would be this guy here. This is a prototype. Let me get it a little bit closer so you can see it, and I can see what I'm showing you. And this is for a police throw phone, and this interfaces telephone lines, and is controlled by a 5-volt controller, and telephone lines are negative 48 volts, and they feature a 121 volt peak 20 hertz ringing signal, obviously not compatible with a microcontroller. So these 4 little guys here are 12 volt relays. It takes 12 volts to operate the core. They're relatively low current compared to the one I just showed you, and these are form C. So they interface our little 5 volt guy here with some relatively high voltages, and this is a ring transformer which generates that 20 hertz sine wave I spoke to, which is 86 volts RMS. So we have a 5 volt proc basically running some relatively high voltage stuff, and we certainly don't want to mix 48 volts into a 5 volt system. That's not good. So that's one of the uses of relays, and also it's good for isolation. Like if you have a hostile voltage or current, you can keep it away from sensitive controlled electronics, and it's very, very robust in surviving transients, say like a spike from lightning or something like that, where a solid state relay, SSRs, which do exist, and for AC they use something called a triac, and for DC they use something based upon a MOSFET. But this is a physical, mechanical switch. So yeah, you don't have to worry about punch through or anything else with a relay, although you can weld the contacts together if you pass a large current through them. So this is kind of a drawing of the contact, and these are kind of like little spring guys that are present in many relays, and the contacts themselves are little pieces of metal which are basically welded onto these springs. So it's not just enough to pull in one of these to touch the other. I mean, it'll work, yeah, for a while, but what really has to happen is it pulls it in hard enough to move these. So in many relays, these are on little spring-like devices, and when they hit, it moves and they wipe. And that's what I'm trying to show here. So the wiping action, where one slides on the other, tends to clear off any dirt or oxides that may form and keep the relay contacts clean. So that's white. Now sparks are usually never good, except if they're in your car. You know, that's what makes your car run. And the reason is that sparks can move metal. So if a relay is sparked a lot, and the sparks typically come from inductive loads, you actually transfer metal, and here what we see is a little divot on this guy and a little hollow point on this guy. And sooner or later what this will do is it'll lead to relay failure, which isn't good. So if you picture a relay and a car production line being controlled by programmable logic controllers, and something's reliably or not reliably turning on a motor or whatever, you know, a technician would have to take that offline and change the relay, because they do wear out with time. Now we also have a phenomenon called dry contacts, and what this means is that they're very small voltages and very small currents, and this is kind of hard to keep the contacts clean. And an example of dry contact would be relays that switch like audio level voltages. Stuff is typically, or could be, under 1 volt and at very low current. So it's kind of good to have current flowing through relay contacts if you want to keep relay life relatively high. Now, to figure out the circuits for this, fortunately, magnetic circuits are very similar to electrical circuits, and I'm trying to compare the two of them here so we can move along and see exactly what happens when we operate a relay. So in electronics, the term is EMF, which stands for electromotive force. Now, this is kind of an older term, and we just talk about voltage, but it's referred to as EMF. In the magnetic equivalent, it's MMF, for magnetomotive force, and this basically comes from winding turns of wire around a ferrous piece of metal, like a nail if you like, and it generates lines of flux, of field, lines of force. And stepping down to the next line, in electrical circuits we have current flow. In a magnetic circuit we have lines of force, which is sometimes called flux. So the more current that flows through a given coil size, the more flux, and that's assuming that the core does not saturate. For example, if I took my relay here and ran this on 220 instead of the 240 rather, instead of the 120 that it's rated for, does not necessarily mean that the amount of flux is going to double. Because when you're dealing with ferrous material, you can saturate it where you can't fit any more lines of force in it. That's not an issue with air, but it is with magnetics. So this flux is going to be the equivalent of current, and then down here, lastly, we have resistance, and we call this the opposition to current flow in electrical circuits. And in magnetic circuits, this is reluctance, and this is supposed to be a script R, not a very good one, I have to say. And this is opposition to flux. So we have things that oppose flux. A good example of a low reluctance piece of material would be a nail made out of metal. An example of a high reluctance would be an air gap. So flux always tries to take the shortest path. So if we look at a magnetic circuit here and compare it to an electrical circuit, we see a lot of similarities. And in the electrical circuit, let's start down here first, is we have a potential of 10 volts, and this is the EMF. And we have a circuit here comprised of the values I made up of 100 ohms and 900 ohms. And as you know by voltage divider is that most of the voltage, 9 volts in fact, will be across the 900 ohm resistor. So in our circuit here, the largest resistor drops the most voltage. Now if we go back up into the magnetic circuit, here we have our source of flux, just like the battery, and our magnetic circuit consists of the relay frame, which is basically low reluctance, it's a ferrous material, and then we get up to the armature here, which is pulled away, and we have a large reluctance up here, which has to do with the air gap. So flux would be basically limited by the large resistance, just like most of the current here is limited by our larger resistor, which is 900 ohms. Now I'm going to make a special resistor here, I'm going to call it the gym resistor, that as more current flows, the resistor drops. There is no such thing, but I just made it up so we'll pretend that there is. So here's what happens. We pass a current through the coil and it generates MMF, a magnetic field. And the magnetic field has lines of force that go from the pole piece to the armature. And if that reaches a certain amount, what will happen is the armature will start to move. It'll move a little bit closer, say right here. Now, as it does that, what happens is that the reluctance of the air gap becomes less because the air gap is smaller. So in our electrical equivalent here, we could now say that this 900 ohm resistance, since we're passing current, is now maybe decreased to 500 ohms. So as this starts to get closer, the flux that's flowing in our circuit here increases. And as it increases, it's going to cause this to pull in even faster and get closer to the pole piece. So a little moment later here, our armature may be sitting at this point, and the air gap is further reduced, hence more and more flux is flowing in the circuit, which means that it's going to pull in the armature faster, which means that the reluctance is reduced, which means that it's going to pull in the armature and so forth until finally the armature is resting as close as it can get to the pole piece. So this is kind of a runaway situation, and in our case down here is what we would be doing would be decreasing the resistance until it's some low value, say 10 ohms. So the principal drop, and this is where the MMF appears when the relay is de-energized, is across the air gap, because that offers the most reluctance, the most opposition to flow of flux lines. So in a way, this is kind of like a mousetrap. If there are no mechanical aberrations here, like a little burr, say, in the hinge where this operates, is once this begins to move, it's going to follow through. It's like a mousetrap. When it goes, it goes. So that's the thought of it. And what that ends up with is that if we were to plot the let me use a different color here, the operation of a 12-volt relay. Let me do it like this, and we'll say that this is 12 volts, and we're going to have two states here. This is a binary. There's on, which means the relay is activated, the contacts are pulled in, and there's off. Now a 12-volt relay means that it's guaranteed to operate at 12 volts. The data sheets may give you values where it'll pull in, kind of. So what we're going to do here is we're going to slowly turn up the current, and we'll just make a variable DC source, and I'm going to draw this correctly as a relay coil. It doesn't matter in DC, but you'll be seeing this in AC anyway, as a situation where the DC current is limited by the resistance. So as we increase this here, we're going to reach a point where the relay operates, and then we'll go out to 12 volts. Now remember at this point that the armature is completely in touch with the pole piece. So a lot of flux is flowing in the circuit, and now as we reduce this, and we'll say that this pulls in at 10 volts, and that associates with some current I that's flowing in the core. Now if we start to turn this down, is what we'll find out is since it's been activated, we can go down, say, maybe to 8 volts before it releases. So what we have here is a little bit of, it's called reluctance. It's the pull-in and drop-off points are not the same. So that's kind of the thought of when we have a system like this, is that as long as we operate in a binary fashion, 0 to 12 volts, we're in good shape. So a circuit would do that, would be this, say plus 12 volts, and this will be our relay, and then we would have, say, a transistor or a MOSFET going to ground, and that would be switching this, and in the case of a bipolar, this would come down to about 0.4 volts, which is close enough to 12 volts. Now, we have to be very careful of our relay transients. So if I take a relay like this, and we'll say we feed this from plus 10 volts to make easy math, and I'm going to put this relay in a dotted line because it has two components in here. It has the windings, which is an inductance, and it also has winding resistance RW, and these cannot be segregated, they cannot be separated. And I'm going to show this as a low voltage switch, which is usually the case, and I'm just going to use a regular switch here to do this instead of a solid state device. Now to allow us to see what happens when the relay releases, because this is when we kind of have an issue here, is we'll let the winding resistance equal 10 ohms. So this is just making for easy math, and I'm going to shunt the relay with a 100 ohm resistor. Now the only purpose of this resistor is to demonstrate what happens when a relay is released. It's really not part of the circuit, it's just to show you there are much better ways of suppressing what's about to happen than putting a resistor across it, which in fact is just kind of a waste of current. So we'll say that the switch is closed, and we'll have some current flowing through the 100 ohm resistor, and we'll have a current path flowing through the relay, plus and minus, and that will be 1 ampere, because after the relay's been on for a long time, the inductance will have 0 volts drop across it. So this is going to be, after a long period of time, we'll have a plus and minus drop across the relay of 10 volts. And actually, if we could segregate the resistance, we would see that that would be across the resistor, but we can't do that because the resistance is built into the wire. So we'll say that it's been on for a long time, and now we're going to open the circuit here, turn the circuit off. And what happens is that when we're putting current through this guy, is that the energy in an inductor is stored in a magnetic field, and this is kinetic energy as opposed to that in a capacitor, which is electrostatic energy or potential energy. So this energy has got to be dissipated, and what will happen is that magnetic field will collapse, and this is when you get a spark in your car. It's exactly the same thing. So one thing we know about an inductance is we cannot change the current quickly. Just like in a capacitor, we cannot change the voltage quickly. So what will happen is that as soon as we open this switch, so there's no more current flowing through the switch, the polarity across the relay changes from plus to minus. Now, this is going to be the voltage and current source for this circuit. So that's going to come from anywhere. It's just what's stored in the magnetic field, and we have to account for all energy. So that'll produce a current flow in this direction, and the magnetic field, when it collapses, is going to be dissipating its energy as heat in the winding resistance and in this external resistor. Now what we know is that if we, at say, sometime here, we'll say that this is T0 plus, we turn off the switch, is we're going to see the current asymptotically decay toward 0. So this will be the current flow of 1 ampere, and it'll eventually reach 0. But to make that happen is we have to now force this current through a 100 ohm resistor, which is going to produce a plus minus drop across the resistor. Now it's incredibly important that you write down the polarities here. And I do this every time I explain a resistor, and students hardly do it. So if the question is what's going to be the voltage at this point when the circuit turns off, you've kind of got to know what's going on here. So what's the voltage drop right here when we interrupt the current? Well, we have 1 ampere flowing still, and this is T0 plus, and 1 ampere flowing through 100 volts will produce 1 ampere flowing through 100 ohms will produce 100 volts in this polarity. So what this point would see then is we're plus 10 volts. Let me kind of draw that as a battery here. 10 volts, and we're plus minus, so this is series 80. So if we were to graph this, and this would be 0 volts here, and this would be the point where the relay opens, is what we see is this guy would jump up to 110 volts. And then, this is our 10 volt source here, it would decay asymptotically to 10 volts. So 110 volts would be at that point. That's a lot. Now, if we make this resistor larger, what will happen is it will get a larger voltage. For example, if I use 1K here, this would now be 1,000 volts. But the curve would be a little bit different. We would jump up to 1,000 volts, through the ceiling here and into the room upstairs, but it would decay like this. So we're talking about 1,000 volt transient. Now the question you need to ask is, what is that going to do to the switch? 1,000 volts is a lot. And probably it's going to cause a spark in the switch, i.e. damage the switch. So what we see here is that the energy has to be dissipated in some manner, And if we're not careful, is we can produce a very, very large transient. Now what may be confusing to you is that it ends up at 10 volts. Now if we consider the switch opened, what we have now is that the relay is connecting 10 volts to the top of the switch, and after a long time that it's been turned off, there's not going to be any current flowing. The voltage drop, DROP, is going to be 0, which means that the voltage on each side of the relay is going to be 10 volts. And the relay's off. So this is a low side switch. So we can generate tremendous transients depending upon the value of our resistor that really doesn't need to be here. Now suppose we get rid of the resistor altogether. We don't have it. All we have is the relay. And let me just redraw that real quick because the sheet is getting kind of busy. So we'll start out with our 10 volts as we did before, and remember this is just like a 10 volt battery, consider a power supply. And our relay, which has our winding, 10 ohms, some value of inductance, L, associated with that, and now we're going to go directly into our switch to ground. Now the minute I open this, is I have 1 ampere flowing in this, and what we know is 1 ampere has to flow at T0 plus. So as soon as this is open, the voltage across the relay switches plus to minus, and it will produce whatever voltage is necessary to discharge that magnetic field. So what we get across here is a lightning bolt until the energy in that magnetic field is gone, i.e. very bad for the switch. Now, let's put a transistor in here. Let's put a FET in there. Yeah, it'll turn on once. When you turn it off, this transient is going to wreck the transistor. It may fail open, may fail short. If it fails short, the relay will stay operating. If it fails open, it'll never operate again. So what we need to do is figure out a way to discharge the collapsing magnetic field without doing anything ungreen. That is, that resistor that I put here before is just wasting power. It's just getting hot, and the only reason it was there is so we could demonstrate what that transient looks like. So the proper way of doing this is to take a diode and put it in this sense. And what we see is that the diode is going to be reverse biased when the switch is closed. So the diode current in this direction, since the anode is more negative than the cathode, is going to be 0. But when the switch opens up, we now have a discharge path, and the drop across the diode will be approximately 0.7 volts. So the diode effectively quenched the transient. So if we look at that on our diagram here, and here's going to be our 1 ampere flowing, and we'll come over to here and we'll call this T0 plus, is that the voltage now, and this will be the current, and I can't even draw it because the diode is nonlinear, but what the voltage would look like at this point, we'll call it point A, be 0 volts, and then when this opens, it'll jump up to 12.7 volts, stay there for a bit, and then decay down to 12 volts like what we had before. Now to get the 0.7 volts here is you need to draw the arrows, you need to mark down the polarities. Let me stick a battery in here to be clear, plus minus. Okay, so the polarities are plus to minus, so they're series aiding, 0.7 of a volt, forward bias drop typical. So this is what we're going to have when we turn the relay off. And as you can see, that this is going to do no damage to anything. Transistors here, as long as it has a breakdown rating of something higher than 12.7 volts, is going to survive very well. Now, like everything in electronics, there's always a downside to something, and the time constant of a circuit tau, and this is an LR circuit, is equal to L over R. Now this kind of seems backward logic, but in fact correct, is that when we forward bias this diode here, is the effective dynamic resistance is very low. So it takes a while for this to actually release. The lower this resistance is, the longer the release time of the relay. So that's kind of an interesting thing. Now, one other point here is when I make up a lab, I try to get double duty out of it. And what I wanted to see here when we activated a relay was kind of the asymptote, where the voltage across it climbed up and asymptotically approached 10 volts, and likewise when we released the relay we would have a decay, which would be an asymptote, and we would use AC circuit analysis techniques just like you did in AC circuits to figure out what the time constant is and all that stuff. Well, time constant equals L over R, but what happens is when the relay releases, when that armature moves away, it changes the inductance of the relay. So we're dealing with two different time constants. One is when it's activated, and the other is when it's released. And what you get in here is this dimple. And kind of took me a while to figure out why that was there. And as far as I'm concerned, it ruined a follow-on experiment for the AC circuits, LR circuits lab. But that's in fact what happens, is we get a delta L when that magnetic circuit changes. Now this is shown as a low side switch. Kind of let's look real fast and see what happens with a high side switch. So in a high side switch, and we'll use the same parameters that we used in the low side guy, is we'll start out with 10 volts here, and now we're going to put the switch up here, and this will go through our relay, L, our winding, and we'll say that that's 10 ohms as it was before, and then we're going to ground this because our switch is going to be up here, and then we'll have our little old resistor over here as we did before, and we'll make him 100 ohms. So we're going to close the switch, and current's going to flow. Let me close the switch here. There we go. Current's going to flow, and this is going to be, after a long time, 1 ampere. After the relay is activated and time has passed, it's going to settle down as being 1 ampere, and there's going to be a total of 10 volts. Well, there'll always be 10 volts across the relay. Now let's see what happens when we open the switch, and we're dealing again with the case of 1 ampere flowing. So we're going to open the switch, and what we know is the magnetic field is going to collapse. So I've got to put this in my little dotted box here. The polarity when the relay is activated is what you would expect, plus and minus, and when it releases, the collapsing magnetic field, and this switch is now open, reverses the polarity of this such that 1 ampere now flows in this circuit, discharging the energy stored in the magnetic field, and produces a plus minus drop across a 100 ohm resistor, and that drop ends up being 100 volts. Now if we take a look at this, since this is now opened, we see that the positive side of this is connected to ground, and we can conclude then that this side is going to be more negative than this side, which means it's going to be negative with respect to ground. So if we take a look now at this point, V, and remember that this can be a transistor, is what we'll see is that this point here is going to be setting at 10 volts. I need to do this a little different. 10 volts. And this will be the point where we turn the relay off, T0 plus. We're going to get a 100 volt drop across this resistor, which means that relative to ground we're going to go down to negative 100 volts. So this side is going to be more negative than this side by 100 volts, and as I said before, this side is connected to ground, and then this will asymptotically almost decay toward 0 volts, And again, when the relay actually releases, we'll get that little glitch in there. So if we have a high side switch, is what we get is a negative going transient. And our concern is for our switching device here, which can be a transistor. So to fix this circuit is we would install a diode with the following polarities, just like we did before. And then that would cause this, when this discharges, to go 7/10 of a volt below ground. So with the diode in here, let's get rid of that guy, is I'll just put down 0.7 volts plus to minus across the diode. So this will drop down to here, remain a little bit, then go back to 0. So it's elegant that a simple diode can do the job here. And in our case, this diode has to be rated for 1 ampere, because that's what the current is going to conduct. And the breakdown voltage of the diode is a, well, whopping 10 volts. And it effectively discharges the energy that's contained in the kinetic energy contained in the magnetic field of the relay. So when you wire relays, you have to be very careful of this stuff, because it can wreck switching devices. And maybe it works fine today, and the next week it fails. So you don't want to have a situation like that, which is a conditionally bad design. You want to be conservative and watch this. And if you put a scope on this point, well, it's possible to damage it. That's without anything here, because you're going to have an infinity if you open this up and there's no path. What will happen, and let me just draw this on yet another page, is we'll have our 10 volts here, and this time I'm going to draw this as a battery. And here's our switch, and this will come over to our relay guy. Put the dots in there and go to ground, and switch is closed. We're going to have 1 ampere flowing again in this direction. And when the switch is open, we're also going to have 1 ampere flowing. So when the switch is closed, the polarity is going to be plus and minus, as we would expect, because this is the load. And when the switch opens, the polarity across the relay is going to change, plus to minus, because now this is the energy source, and it's going to have that 1 ampere flow through the battery up, and guess what? Through the switch. Lightning bolt. So it'll be a very fast discharge, but you're sparking this, and if this is a solid state device, most likely you're going to wreck it. So in either high or low side switches, for either positive or negative supplies, you'll always have to be careful of transients. Now you may say, well, who cares about a negative supply? Well, let me give you an example of that. And the cool thing about this is that these examples work. The circuit analysis, which is the key to this, work no matter what. So we'll show this. Well, the camera ran out of memory, so we're continuing with negative supplies. And here I've got my circuit here, a 12 volt source. Notice that the positive terminal is grounded. And if you think negative supplies are kind of unrealistic, that's what telephone company plant operations operate on as a negative 48 volts. So here we have an unprotected circuit with a relay, and when I close the switch here, I have a through path, and notice that the winding resistance is 24 ohms. So what's going to happen is that the current will rise in accord with the LR time constant, and it's not going to be per se the exponential that you're used to seeing, because as soon as the relay operates, the reluctance of the relay changes, the core, and that changes the inductance, which changes the time constant. So it's not, it'll have a little bump in it if you're actually looking for a current charging constant, kind of like this. This would be 500 milliamps here. It would start up, and then be a little dimple in it, and it would continue to asymptotically charge toward that. So anyway, we have a circuit, and our current is flowing in this direction, and suppose we open the switch. what happens as before is we have an immediate reversal of potential. So now this would become plus and this would become negative. Again, current through an inductor does not like to change like voltage across capacitor. When we close the switch, we built a magnetic field, and now that we open the switch, the magnetic field is collapsing. Current has to flow in the same direction, which is going to be this direction, and what we end up doing here is sparking the switch. What this would look like from the standpoint of, say, a scope, if it's operated at this point here would be negative 12 volts, and here's 0 volts, and then when we open the switch, we get a transient, which theoretically would be up to infinity. Realistically, it would arc across the switch, and that would act like some kind of finite impedance, and then drop down to 0 volts. So, very, very damaging situation when you have a lot of voltage causing arcs like that. Now let's protect the circuit, and we're going to put a diode across it and see what happens now. So we'll say the switch is closed, and what we have is a conventional current flowing in this direction as we had before. Close the switch there. And notice that the diode is reverse biased. Kind of important, because if you get that diode across the battery, well, bad things are going to happen. Either to the supply, I'm showing a battery, or to the diode. And the drop we're getting from this is plus to minus as would be expected. Now when we open the switch, the polarity across this reverses, so that would give us plus and minus in this direction, and then the discharge path for the current would be through the diode back through the relay. So looking at this with a scope is what we would see as before, is when the relay is operated. We'd be sitting here at this point at negative 12 volts. Now when the switch opens, it'll pop up to approximately 0.7 volts and then decay down to 0. So that huge transient which we had before is no longer. The release time of a relay is going to be longer the lower the impedance path of the shunt, because the time constant is L over R. So as R goes down, the time constant goes up, and that may seem to be kind of funny, but they actually have slow release relays based upon this concept. So what kind of diode do I need? You're thinking when you look at something like that it must be really, really big, and not the case. To get it in this circuit here, the PRV, that's the peak reverse voltage, has to be greater than the supply voltage, 12 volts. You always want to be conservative. 50 volt diode sounds nice, common breakdown voltage. And the forward current has to be greater than 500 milliamperes, which is what it's going to have to conduct on the instant that the switch opens. Now realistically, 1N4001 is a 1 ampere diode, continuous, and the surge on that is 35 amperes for a short period of time. So you have all kind of wiggle room on your diode. So that'll conclude for relays, and specifically dealing with a negative source. And thank you for watching.